All right, I was told to start on time. It's 3 o'clock, so let's get into it. Welcome everyone, I'm Milian. Nice to see you all in my talk. First time in Norway for me, pretty nice, I have to say. And today I want to talk about profiling tools, and especially two of them, which I actually wrote myself. And those two are, in my opinion, sufficient to solve, I don't know, let's say 90% of the performance issues that you usually see in off-the-shelf embedded kind of UI projects that we often deal with at KDAP. And both of these tools that I'll show you are free open source projects. You can just go use them. And I kind of see it as a pragmatic introduction into profiling because at least where I'm standing, I still see far too many people not being aware of the tools that are out there and then struggling essentially with being able to find performance opportunities to improve the performance of your applications, right? So let's get into it. I'm going to start with a short introduction, then we'll talk about Hotspot and Linux perf. So this is definitely a Linux-specific talk here. And inside that first section, we will essentially solve or look at two sides of a coin of an application, basically. One is the behavior of the application while it's running on CPU, and then the often neglected, in my opinion, view on what it is doing when it's not actually running and why that is and what you can possibly do about that, right? We'll finish off with a short summary of what you would need to do to actually use these tools in an embedded Linux context. And then the end of the talk is going to be about Heaptrack and looking at heap memory consumption and similar or related metrics that give you maybe another inspiration of how you could improve the performance of your applications. Alrighty, so let's start with the introduction. Why are we even using profilers? And you don't need to read this code. It is pretty, well, stupid on purpose. But the inspiration for this slide, or this specifically bad code, actually came from a code review I did the other day. So it's not that this is completely made out of the blue, but I still see people writing code like that. And now this is just one slide, and eagle-eyed people in the audience are probably will scream at me. It's obvious what the problem is. The thing is, imagine that you are inheriting an old code base, and this is somewhere hidden deep inside 10 layers or something of 10 million lines of code or something like that. And you're tasked with make it faster, please, because we don't know what to do. This is often the problems that we get thrown at being a consultancy company. And then go in, we use the tools, we hopefully find these very obvious performance issues, and then we solve them. Customers are happy, consumers and users of the software become happy, everyone is happy. Great. Let's see whether we can do that. And the idea is when we start with that and use our first little kind of profiling utility called perf_stat, we can very easily measure on a large scale from the outside, similar to time, a bunch of performance metrics already. And I won't go into details here, but perf is awesome. The thing is, though, when we start off with a super trivial example, it's really, really slow. We just enter 10 million items into a hash map. How could that possibly take us 4 seconds, right? This is nuts. It's really, really bad. But there are two things we can improve easily, guided by a profiler. And one of them would already make it roughly 4 times faster. We'll go into that and figure out how we can find that. And then once we have solved that one, we would rinse, repeat, and then hopefully find another very stupid code path here that would allow us to make it even faster, and then another 2x speed up, roughly, right? The numbers don't really matter, but the idea is I, as a software developer, often fail at realizing what kind of impact the code has that I write on the actual runtime. So whenever you're talking about performance or Klaus used the word P-word. We are all C++ developers, right? And in my opinion, oftentimes those folks that actually attend a conference, they are above average. But we often have to deal with lots of people that simply don't care about performance. They just want to ship their features, right? They don't spend days probably to figure out the impacts their code has. And then someone else has to clean up. And maybe that's your role then in your company. And with these tools, you can actually easily do this kind of cleanup and hopefully teach your colleagues then to behave better and so forth. All right. So, as I said, we'll look at 3 kind of topics on CPU profiling. When is it running? What does it do? Off CPU profiling. Why do I get switched out by the kernel? Why am I sleeping? Where does this happen? And then heap memory profiling. How much memory am I using on the heap? And why are we allocating so much and so often? This talk here is specifically meant for Linux, right? So what I'm going to teach you here doesn't really apply to macOS or bare metal deployments or whatever. It really requires you to use Linux. We are going to concentrate on what I term these single non-distributed systems. There are solutions for server fleets. If you have that, look for that. This is not this talk here. I'm more looking at you have maybe a couple of processes talking together, but you have one little machine that you can focus on, right? And there are a lot of projects out there that hit right down in that, or that match this bucket. I do mention embedded in the beginning, but quite frankly, all that I'm going to show you applies easily to normal desktop applications and even server applications if you want to. The embedded twist is simply how to make these tools usable in an embedded context. We will concentrate on compiled system languages, so my slides will use C++, but the tools will just work with any normally behaved language, I would say. So Rust will work, Fortran will work if you want to do that just fine. But as soon as you go into the more, well, managed languages or something like Go that decided to not follow the standard ABI, then you're on your own basically, and you will have to use a different tool. Or in the case of Java and Python, and even V4 and QML, there are sometimes tricks that the VMs give you to essentially get some knowledge of what is happening with that within their managed environment, such that you can still use Rust. But I won't go into that realm. But if you're in the above camp, this is the right talk for you. All right. Now, let's start and talk about the first tool, Hotspot and Linux perf. So before we go down there, just as a common remark, I hope all of you are aware of that. But when I look back at myself, when I started writing C++ code nearly 20 years ago or so and did my first profiling attempts, I simply wasn't aware that compiler optimizations and debug symbols are 2 distinct things that you can toggle individually, right? If you're profiling, make sure you have both enabled, right? You definitely need the debug symbols and you definitely want to have your compiler optimizations enabled, because otherwise this claim of C++ being a zero-cost abstraction language is far from true, right? It's a lie. But as soon as you do enable compiler optimizations, now we are talking, right? So don't repeat the work that your compiler can do for you. Make sure in CMake world, for example, to use the rel with dep info build type. Never ever use release, because that's simply unusable. You won't have any debug symbols. I don't know why or who came up with that idea to add that. It's completely unusable. And when you're using Rust, and I'm happy to see more and more people talking about Rust here at this conference, I like the language myself. Thing is though, you have to do some more manual fiddling with the configuration. It's all publicly documented. It's not a secret or anything. You just have to be aware of it. Follow that link, follow the documentation, basically how to get such a build configuration up and running. And then at least where I'm standing, quite often we still consume code from elsewhere, like for example from your Linux distribution, right? And historically, it has been quite the problem to figure out what the hell is going on in that external code that I pull in. Thankfully, since a couple of years, the Elf Utils project has created this thing called the debug info daemon or D that is a server that you can set up very easily by setting this environment variable locally for whatever distribution you're using, and then transparently most of the tools, including the ones that I'm going to show you, can pull debug info from that server behind the scenes, and you will see actual function names instead of question marks, which is a great win in my opinion. Okay, so Linux perf. That is a whole tool suite of performance-related tooling inside the Linux kernel. It's split into two. On one hand, you have a bit of stuff within the kernel space itself that actually, for example, programs the performance monitoring unit or the actual hardware to enable us to get things like the sampling profiler up and running that I'm going to talk about next. That code is very platform specific, but the good news is that it's supporting basically all the hardware out there. Like you can use it on Apple ARMs even, and RISC-V and MIPS and AMD and Intel and you name it. You just basically need to have a piece of hardware that actually comes with a PMU. So, and a working PMU. In our world, we often had customers using IMX6. Anyone ever targeted that platform, ARM IMX6? Good on you. That actually had a broken PMU, for example, that only worked on one core and not the others. Anyways, this is the kernel side. And this is then accompanied by a bunch of tools in user space that, on one hand, drive the recording mechanisms inside the kernel. This is essentially perf record. And we'll stick to use that to actually record our data. And then there are also a bunch of tools that then analyze that data, such as perf report, which is doable, but I give a training on these topics and debugging tools. I did that the last 2 days here at the conference as well. And back when I started giving this training, that's what we had. And it was so hard to teach people how to actually make sense of the data using perf report that at some point I realized, you know what? I'm going to save myself some time. I'm going to write a new tool called Hotspot, which is a graphical interface that analyzes the data. So it's essentially a drop-in replacement for perf report. And we're going to stick to perf record for actually getting the data. And this is a free open source project sponsored by my company, KDAB, that I work for. And it is pretty easy to use, as I'm going to show you. But it only touches the surface. Perf can go way deeper if you want to. There are a bunch of low-level features that I'm simply never using myself. So, as I said, this is a pragmatic approach. For the 90% happy case, this is going to be sufficient. And if you want to check out, the code lives on GitHub, KDAB, Hotspot, follow us there. All right, so let's have a look at some on-CPU profiling. And this is what I wanted to show. All right, so what we are going to look at first is our code, assuming it actually runs on the CPU, right? So this is something where we are not sleeping, where we are not suffering from lock contention or anything like that. This is our inner kernel or our normal graphical application rendering something, you name it, right? And then what we are going to use perf for is essentially driving a so-called sampling-based profiler. What that means is basically just regularly have a little code monkey in our machine that runs like as if GDB would interrupt your application regularly, and you look at where am I, right? This happens by sampling the so-called instruction pointer, and that value, this address, can then be mapped to, using the debug information, to a location inside your code, right? And this is already great. This is awesome, because then we can actually see where we are at But you have to keep in mind this is a statistical process, right? You actually need to collect a bunch of samples to have a sufficiently sized population to make any sense of the data. Yeah. And what we're going to do using perf is basically behind the scenes, it's going to program the PMU to interrupt your application every millions of cycles, or roughly something like that. But what we're going to tell the tool by default is give us 1,000 samples per second, roughly. If you actually look at the data, you will see at the beginning it will try to figure out the right cycle value such that it approaches the steady state of about 1,000 samples per second. And the good news is that this sampling-based profiling approach actually is driven by the PMU, meaning we get hard numbers directly from the hardware. That is not a lie. So in case any one of you remembers using Valgrant's Callgrant or something like that, that has been quite popular back in the day when I started for profiling on Linux, that actually did not look at the real thing. It measured instructions and then had a software-based simulation that tried to translate instructions into actual cycle costs, but it was always completely off and never really reflected reality, whereas this actually reflects reality. And the sampling-based approach it has really, really low overhead, so it's super easy to actually use this even on large-scale real-world applications, even on embedded. But this is crucial for you to understand. We do not actually measure per function time. And there are some sampling-based profilers like vTune out there that actually are a bit deceptive in that regard, because they would tell you this function consumes 100 milliseconds or something like that. But that's not the case. What we can only say is, statistically speaking, this function was running for 10% of the samples or something like that, right? So very important to keep in mind when you use these tools. And if you would essentially want to do that, all you had to do is run perf record and then my application. Problem is, this is completely useless. Never ever do that, in my opinion. The reason is you would not actually have stack unwinding enabled in this case. And stack unwinding is crucial when you actually want to understand your code base and figure out where in the code you can actually change something such that you have a significant runtime improvement afterwards. The unwinding essentially, it means I cannot just look at the instruction pointer. I also need to figure out where this piece of code that I'm currently running was called from, right? Because otherwise, in the normal applications that I deal with, you will have a bunch of samples in malloc, in memcopy, in memset, right? And it's like, yeah, cool, but what should I do about it? I cannot go into libc and actually make memcopy faster, right? Would be cool, but definitely not what I'm good at. Instead, I need to figure out where do I, for example, accidentally copy my std string that then triggers the memcopy, right? So I need to unwind the stack to figure out where this is coming from. And unwinding is also a crucial ingredient to producing so-called flame graphs. I will go into this visualization in a bit, but the gist really is, without call stacks, so the command that I just showed you before, if I would just run perf record and then visualize this in a tool like Hotspot or using one of the flame graph scripts, then I get this really, really flat flame graph that basically has this problem that I described earlier. You just see malloc and friends, but you don't see where it is actually coming from. So what I actually have to do is I have to enable call stacks using, for example, call graph dwarf. So this line is actually more or less the default that you can remember. If you want to actually get something sensible out of the tool, you would run perf record -- call graph dwarf and then the application you want to profile. And then when you visualize this, you actually get these flame cities, skylines, whatever you want to call it. We'll get into that in a bit. So that said, let's try to make this more actionable and actually go into a demo here. I said we are going to run perf record -- call graph dwarf, and then my little application that I showed initially that took us roughly 4 seconds or so. And now I actually collected roughly 17,000 samples. And because I used this call graph dwarf, each of this sample will have a tiny copy of the stack associated with it. And then I can use Hotspot to look at this perf data file here that was created, pretty large, 136 megabytes. And now at analysis time, it will go over all of these samples and then unwind the stack using these tiny copies of the stack that were associated with the with each sample. And now this is a flame graph, and the width here, the x-axis, has no meaning other than 100%. There is no time axis or anything like that. And because this is a statistical process, what we are going to do is essentially we look at the number, how many, what fraction of the samples had a given function on the stack, and this is then your cost attribution. So basically, you can have the same view of data using these tables, and as you can see here, start had a cost of 95%, and then you go down and down and down, and then this has 80% of the cost, meaning here in this view, it would have 80% of the width. And this is a really great visualization invented by Brandon Gregg that really makes analysis of performance data so much faster. And the way I always teach people how to use that is basically you start from the top and then go down and you try to find code that you have under your control. And very important is that all of this is interactive, right? So one thing that I want to show you here is changing the color scheme, because the default color scheme of a flame graph has no meaning. It's just flame-like looking colors. If you switch to system, then we try to basically distinguish between code you include externally and code you have under your control. Now, inlining will always happen or trigger code being put into your binary, so they will still be shown as your code, and it's probably hard to see on the projector. There is a distinct shade of yellow. Main is a bit darker than the inline stuff above. And then with a bit of looking, you sooner or later find code like this here that says data stringify inside computing the hash when we mplace. So this is probably pretty bad. I can do something like see or search interactively in my flame graph where this is happening, and I see it popping up in 3 different locations, right? I can go to my caller callee view and do a data stringify, and this is now essentially aggregated over all the call stacks and whatnot. And this is a very common approach to using these tools. So you would slice and dice the data in different forms to find code that you have under your control to then hopefully speed it up, right? And as I said, initially we start off with the 4 seconds, right? And now here, sooner or later, we found this function, data stringify. I can do something like view caller callee on the right click on that one. And now here inside the caller callee view, I have a source code location. Open it in the editor, and I'm directly at this location here, right? Similarly, whoops, that was the wrong shortcut. I can go up 1 step and see where that one is called, maybe sort by the cost, open that location, and now I see that someone was lazy and essentially implemented the hash function by hashing the string of this class. And you cannot imagine how often I've seen this. It's really, really bad. Please never, ever do that. It's super slow, right? So one reason people do that is that there is no easy hash combine yet inside the standard. Thankfully, we have boost hash combine, for example, so please use that one. I'm not going to pull in boost here. I'm just going to do what boost would do more or less manually or something like that. essentially, instead of really computing or building a temporary string, which requires memory allocations and whatnot, I'm going to just compute some hash value directly without any further runtime overhead. So I did that now. I can recompile and I can run perf stat again. And now with this super easy change, we made the thing roughly 4 times faster. And this would work in large scale applications. And this is really the bread and butter of on CPU kind of profiling. There is no more magic than that. And the juice is basically spending the time inside the profiler UI to figure out where you have, where you get an idea of what you could possibly try to do. And it's amazing how often, especially in old code bases, you have problems like this lurking because people simply didn't care. All right, what do we do now? Well, let's just run perf record call graph dwarf a second time on the optimized version. And this is now your loop, essentially, when you do profiling. Usually it's not that brutal, like a 4x, right? Maybe you have 10% there, 1% there, and it adds up over time. And you just go through this again and again and again. And if we do this here, the view looks different, obviously, now. And what we can see when we spend a bit of time is that emplacing is still costly, because what we are doing here is we still construct strings which allocate memory, right? And then when we destroy the set, then we actually destroy strings. All of this is interactive. If I click here, you may see that more easily. These are string destructors inside my data. And if I look at my code, this becomes pretty clear. My struct has a std string in it. I mean, yeah, sure, no wonder there. But down here, I put a const.cal pointer into that one. So even here, emplacing that would trigger 10 million allocations already. And it's pretty easy to just say, you know what, I'm going to use a string view, which actually makes stringify a bit harder to implement because there's no operator plus yet for string views. Colleague of ours thankfully got that one into C++ 26 now. But let's ignore that one. We don't need it anymore because we don't use it in our hashify anymore, right? So a second line change, I can rerun our perf stat command, and now it's another 2x faster. And this is basically all you need to be aware of when it comes to on-CPU profiling. Now, thing is, always copying the stack with each sample, especially on embedded devices, can be quite costly because these data files become really, really large. Thus, if possible, have a look at whether you can leverage frame pointers. And in Yocto, for example, there is an approach to do that, and in Rust it's even easier, because then the data files will become easily 10 times or 100 times smaller. Similarly, what you can do and should do is enable compression using the -z at perf record time, and this will magically, using Meta's Z-standard library, reduce the size of these record files by a factor of easily 100 or so. And that can make or break the tool, especially on low-end embedded devices where you often have really slow flash chips for disks, right? Or you want to right away transfer the data using SSHFS or something like that. So make sure to either use frame pointers, if possible, but my system, for example, if I would look at the current state here with dwarf, then I have a nice flame graph. It all goes into star, except for this bit at the left. We'll talk about that in a bit, but this looks nice. If I instead use call graph fp and look at the flame graph, then it's completely broken, more or less. There's stuff here that doesn't go into main. There is stuff here that goes into question mark. It's utterly broken because that system doesn't use frame pointers yet. So if possible, use them. If not, stick to dwarf. It's a safe thing, but then enable compressions. And now, a dirty reality that I don't want to shove under the rug is that you will always have a bunch of samples that are completely broken. You cannot unwind from them properly. And the reason is manifold. I listed a bunch of stuff up there. My suggestion here is live with it. In the past decade or so, I've used this tool for great effect, even with this problematic area. But for reasons, there is not much we can do about that. Hotspot also has a bunch of new cool things that many people are not aware of. For example, we have this Godbolt-like integrated disassembly view that is interactive, with which you can essentially interpret your code and see how each line of code maps to individual assembly instructions if you want to go dig that deep. And then the costs are attributed also to the annotated source code on the left-hand side, you name it. So have a go, play around with that. And specifically for Rust, so this all works with Rust. We have a Rust demangler built in and whatnot. I actually realized that for complex control flows that you often deal with in the callback-based way you write Rust with lots of functional programming and lambdas and whatnot, it became pretty hard to figure out where inside your code you are actually spending costs. And thus, I recently added the so-called by file aggregation, which really looks at individual files and then easily shows you in this file at that line number overall aggregated, these are your costs, either self or inclusive, right? So this is very, very great for complex control flows when you just want to hone in on a certain file that you're currently editing. Makes it very easy. So this is my summary for on-CPU profiling, and basically the recommended way to run perf record using Kongsberg Wolff, and then the .8192 increases the size of each stack copy to prevent the chances of unwinding, breaking the ceiling there, and then -Z for compression. This is it, basically. And Hotspot is a great replacement for perf report or the flame graph script, and it's all interactive, as we'll see in a bit as well. So let's switch gears and have a look at on-CPU profiling instead, because what we looked at so far is this happy case where we have a task or individual thread or something like that running, meaning we are not scheduled out. But this is usually not the reality, right? We are not working in a vacuum or something like that. We actually very often try to open a file, right? And then the kernel will say, yeah, sure, but that's going to take a while. You can go to sleep and another program can run in between. So you will be put to sleep. You will be switched out. And then at some point, the kernel will decide, you know what? Your data is ready. I'm going to switch you back in, and then you can continue working. And more likely, you even have multiple threads, not just one, right? And then you have to figure out why and how they are interacting. Maybe there is mutex lock contention or something like that going on. The thing is, though, sample-based profiling and most of the tools out there, they only concentrate on these green areas, and they completely neglect the off-CPU time, even though that can easily have a huge impact on the overall runtime, right? So you always have to be aware as a developer whether you're suffering from a non-CPU or off-CPU problem. So let's see how we can handle that. What we have to do now is pretty arcane. You don't have to remember that, as I will show you, but the gist is with perf, we can also not just do sample-based profiling, we can also use tracing capabilities built into the Linux kernel, and then get notified whenever there is a switch, scheduler switch. For privacy, or not, for permission reasons, we only get to know that we get switched out. We don't get to know when we get switched back in, which is bad, right? That means we cannot compute the time that we slept. Thankfully, there's another switch events kind of toggle that we have to pass, and now we can actually come up with a time that we spend being switched in and out. And when we say -- call graph dwarf, we actually get for the first time for the case for the scheduler switch event, the backtrace when this is happening. For example, because we entered a nano sleep, right? So being able to look at the call graph for a switch event allows us to semantically annotate why we are sleeping, be it preemption, be it a I don't know, page fault, a serial I/O operation, network polling, you name it. All of that becomes clear once you look at the backtrace. And then maybe you want to actually combine this with on-CPU profiling, such that you can holistically view both sides, right? The green and the red area, the running and the sleeping area. And then maybe even you want to record the CPU for every sample, such that we can actually see CPU migrations when our task gets moved from one core to another, right? Maybe that's also something we would like to have. And this is quite a mouthful, I agree. If you want to run this, then, wait, let me make sure there's nothing here. If you open Hotspot, you can actually go to record mode, or you can use the file record data. And in here, there's a little checkbox called off CPU profile. You could just use that one to record the data. And then it would do all the stuff that I showed you on the slides behind the scenes. Or you just put it into a script. This is what I did. And I think one of the later slides shows this as well. So now I can say perf profile let Mandelbrot concurrent, which is a tiny example from the workshop that I gave the other days. And I recorded a bunch of data once again. I use Hotspot. And now I have my flame graph as before. And the important bit, though, is that I now actually have multiple metrics. I have the cycles giving me a view on the on-CPU time, right, as before. I have scheduler switches, which is the number of switch events, not so useful. But the way we recorded the data allows us to, at analysis time, compute the off-CPU time. And this is now very interesting, because that's where we actually sleep. And once again, this is something where you can change the color scheme to make it apparent that there is a bunch of call graphs here that we do not have under our control, right? Because there's no yellow in there. This is all system stuff. But apparently inside the middle here already we see first pass Mandelbrot row. That's something that we have written. We can go view caller callee, and then you often have to resize these tables, especially when you have increased the font size for giving a talk. And then sort by off CPU time here. And we can do right click, open an editor. And now it jumped right away to the lock guard that triggered a lot of mutex lock contention, right? And this, again, would work for everything. It would work for page faults. It would work for serial I/O. It would work for large code bases with complex locking hierarchies and whatnot. And this is really a game changer, in my opinion, when it comes to profiling the off-CPU data. So obviously, this is very, very intentionally bad code. We reduce the scope of the mutex instead of just locking it right away. And then we can recompile, rerun the profile measurement, run Hotspot again, and then look at the data again inside my flame graph. And this is the cycles view again. It's the on CPU stuff, but instead I want to switch to off CPU. Let's switch the color scheme again, and we see, yeah, there's still probably some areas where we are still locking on the mutex, but it's much reduced. And what you have to keep in mind is there will always be situations like here where you will have threads that just don't do anything, and that's good, right? Off CPU time does not necessarily mean you are doing something wrong. Quite the contrary, right? If you look at things like a dbus connection thread or some Wayland event threads, I didn't interact with the thing graphically. It was just a tiny benchmark. It's good that these threads didn't do anything. They slept. But now I can say, you know what? This is cool. I want to exclude it from the top. And everything inside Hotspot is interactive. So you can just right click and say, exclude this thread. And then maybe even that thread, right? Let's exclude that one as well. Or you are saying, you know what? this area down here is interesting. I select a bunch of, like a time slice, and then filter in on that area. And then all the data on top on all the aggregations will adapt accordingly. And I can zone in and hone in on the area that is actually interesting to me. And doing this kind of analysis using the command line is super tedious, right? So UI makes this much more of a breeze. And also when I now hover stuff here, this is interactive. And the cool thing is, actually, let me reset all of that. When I look at these orange bars here down there, they are actually the times where a sample was recorded. I see that the main thread is running, then apparently it's mostly not doing anything, and then it's running again. And if I look down here, my pooled background task threads, they're running after some time when the main thread has essentially given them some work, and then they go to sleep and don't do anything. So this kind of area where you now see here's a thread sleeping and there's another thread that actually runs allows us, when we go back to the on CPU view, to figure out why is this code not running on multiple threads, right? And I can say, you know what, let's have a look at this area. What's happening there? And by filtering, I directly see, oh, there is this second pass Mandelbrot thingy. Let's see where this is being called from, using the same approach that I used before. And I realize, oh my God, I was stupid. I forgot to actually parallelize this code base, right? I should actually distribute this work similarly across my worker threads as I did before. So normally this is obviously not that easy, but this is basically Amdahl's law in action, right? The more you try to use parallel multiple cores in your application, the more you have to take into account that serial portions of your code will start to dominate drastically, right? And with this holistic view that you can look at both on CPU and off CPU, you can actually figure out where that is happening and fix those situations to hopefully get better scaling the more hardware you're throwing at your problem. Now, it may happen when you run this that you get warnings or errors telling you to check I/O CPU overload. And this is a very bad thing, because perf is written in such a way that it will never try to stop your system. It will rather just drop events. But you can imagine when you're dropping an event that tells you I was put back to work, like there was a switch in event, then the whole analysis will break down completely. Meaning, if you do off-CPU profiling and you ever see these warnings, then you can essentially drop the analysis. You don't need to continue because it's not trustworthy anymore. Thankfully, there are ways to battle this, and one I mentioned already is essentially enabling the compression, and you can also try to increase the buffer sizes, or maybe use frame pointer unwinding, or you artificially reduce the scope of your benchmark or application to just use a fraction of the CPU cores instead of all of them, something like that. So, summary when it comes to off-CPU profiling is using this tightly integrated scheduler switch trace points inside the Linux kernel allows us to get a really deep understanding of when and why we are being put to sleep. This works with everything. You will find sleep statements like we've found far too many times. Like, people ask us, the boot time takes 5 seconds for our application, then you profile it and you find a sleep for 5 seconds and something like that. And it's like, why did you put it there? Oh yeah, I forgot. That was 10 years ago. And remember that not every source of off-CPU time is necessarily bad, right? But with the interactive filtering, you can filter out what you don't care about and combine the two sides, on-CPU and off-CPU time. It's pretty cool. And quite frankly, I still don't know of a good alternative to Hotspot when it comes to this kind of off-CPU profiling. We may be able to get that using perf record off-CPU natively directly within perf, but sadly this requires frame pointers because of eBPF, and that makes it unusable on my system today, hopefully not in the future. Save yourself some typing, put this into a script like I suggest here, or use the perf record capabilities inside Hotspot, and then don't need to remember all the arcane command line switches to make this workable. All right, now actually using this in a embedded platform setup is not too bad, except when you deal with virtualized environments. So because we actually want to use a PMU, you won't have a good time using VirtualBox, for example. And a lot of customer projects we've seen, they essentially enforce all the developers to use a Ubuntu virtual machine or something like that for their development purposes. And that utterly breaks the cycling-based profiling. There is a timer-based fallback, but it's way less accurate. So if possible, get a bare metal installation of Linux, and then you will have a much better time. That said, tracing and off-CPU profiling inside the Linux kernel is obviously not affected by that, right? It will work just as well in a virtualized environment. And other than that, what I did here live was on the desktop, but in an embedded context, you would basically split this apart. You would run perf record on your embedded machine using SSH or something like that. Hopefully you have a working PMU, and hopefully you don't have these fancy big little architectures. They are supported, but they are much harder to analyze because you essentially get different kinds of cycles. And the important bit is you just need perf there and the binaries. You don't need the debug information. You record your perf data file, and then you take that one and possibly the KAllSyms, the kernel symbol mapping from that machine, put it to your development machine where you have the SDK from Yocto, for example, set up with the debug information and the sysroot. Maybe you have a path to a side-loaded app that you deploy directly using SSH to the device. You specify the paths to all of these things when you run Hotspot, loading the perf data file that you downloaded directly from the machine, and then it just works. It's really not rocket science. And if you have any questions, look at the documentation, reach out. It just works. Now, this is Hotspot on CPU and off CPU profiling, and that's really the most important tool there is when it comes to profiling and performance optimizations on Linux. There is one metric you cannot easily measure, which is the memory consumption, thus Heaptrack. And beyond that, getting essentially slapped in the face by some hard metrics, such as, for example, you are triggering 10 million memory allocations at a certain location, helps me as a developer come to ideas of how I could possibly optimize my code, right? So this is why you often will have multiple profilers looking at your code to get an inspiration of what you could possibly try to do to improve the runtime. So, Heaptrack, another project by myself, which is also sponsored by KDEP, but it's also part of the KDE project. And it's basically a much faster Valgrind massive thingy for profiling memory consumption. What we are doing essentially is we intercept every single malloc event that you trigger, so malloc, operator new, realloc, all of these things. And then when that happens, we also collect the call stack and write that to a file, and then later we can analyze that. And this allows us to gather already 4 metrics: heap memory consumption over time, leaked memory, number of allocations, and temporary allocations. Running this is super easy. We just run Heaptrack, some application, and we would see in the original file the example that I gave that I optimized using Hotspot already, that we initially triggered more than 40 million allocations because we triggered a stringify operation inside our hash map, which is obviously very, very bad, right? And remember, we only entered 10 million items into our hash map, but we triggered essentially more than 4 allocations per entry there. Very, very brutally bad. But yeah, let's actually try and play with this now. I have 12 minutes left. That should work. I have a little example from our wait a minute, let's clear that. From our workshop material. I just run this example 2 times in a benchmark mode, and we see some statistics from Heaptrack already. It will tell you how to analyze the file that was created, and actually it will do that automatically behind the scenes already. And you can look at the summary, you name it. I will jump over this a bit. The interesting bit is basically that we have time-based graphs, and those are interactive. So I could now say, you know what, I want to see the delta between this area and that area. I can say filter in, and now it would essentially 0, 1 value and go until the end. But let's reset that. Or I just look at the whole thing, and this is a benchmark mode. It does the same thing 2 times. And memory consumption going into the upper right corner is very bad, right? This is not a stock graph of your own stocks, right? This is not what should happen. It should go up and down and up and down. But this is clearly an indication that we have a memory leak. So how can we find that? We can go to the flame graph and look at the so-called memory peak consumption, which is, in this case, at the close to the end. And in other applications, could be somewhere in the middle. It's literally the slice of the peak of this graph. And then we see directly, oh my God, there is a function called starts with. Let's right-click, view color, same kind of approach like Hotspot. I mean, I'm the same guy who wrote this. So you will find this code now, which is very, very stupid, right? I mean, starts with definitely should not be that complicated. I created this example, I believe, 10 years ago, where we didn't have nice things yet. Nowadays, we have nice things. We can actually say, starts with needle. It only took us until C++ 20, I believe, to finally get this, right? So we fixed the memory leak, hopefully. Let's rerun and see how that looks like now. And this is now much, much better. It goes up and down, right? So cool. We solved the memory leak in this specific example, but there is probably still some leaked memory. This is essentially the slice of this graph at the very end at the right-hand side. And if we look at the flame graph, it's just 22 kilobytes, so you can barely see this because this here is 1 megabyte. So it's very, very tiny amount of memory that we are leaking still. And this is like in third-party libraries, we don't bother. Let's ignore that. Instead, let's talk about allocations and temporary allocations, because due to the fact that we are collecting every single allocation being traced, we can also count how often that happens. And these are extra metrics that allow us to find opportunities for further optimizations. You would find those things probably if you look using Hotspot and sampling-based profiling as well. But this is like a more direct, in-your-face kind of representation of this data. And allocations, as you might guess, is just counting how many allocations are done. And temporary allocations is a trivial heuristic which simply looks at the data file of the event stream of our allocations and sees an allocation was directly followed by its deallocation. I ignore time and everything in between. If an allocation is followed by its deallocation, I call this a temporary allocation. That's it. And this is good enough to find all kinds of sources where we make stupid mistakes. Like in this case here, when I right-click, view color, I can sort by temporary, look at the file again, and I see this line here seems to trigger a bunch of temporary memory allocations. So let's have a look at the starts with, and hopefully at that point, I realize, oh yeah, this is really, really bad. I forgot the const ref here, because I take these strings by value, they are being copied in, which is stupid. Thankfully, that's something that clung-tidy will also find nowadays for us statically. So please have a look at clung-tidy as well. And even with the const ref, it wouldn't be perfect. But if I use a string view, it actually is perfect, because this string here is on purpose chosen to be very long. So even if I would use a const ref string, then this large string would be put at runtime into a std string, which does not fit into the small string buffer optimization, and then would trigger an allocation. We would find all of this using the tool. And another thing, if we look at allocations and jump to this line here, we will find that this pushback of an object is triggering a ton of allocations. And what we should see here is that we invalidate the object right after pushing it in. And that's one of these cases where I'm not sure whether Clang Tidy will already find it for us automatically, but with a bunch of time, I hopefully figure out that, oh my god, yeah, instead of copying the data into the container, I can actually move it, right? And I will do that using std exchange instead of move, because I like that one much more. I might need to include utility here. So beforehand, I literally did the same semantically, but this is much, much faster, because instead of having to copy the data and then getting rid of one copy, I just take the data, move it directly into my container, and we are all happy. So this is basically the value proposition of Heaptrack, that you can find all of these things hidden in your code bases. You can, if you want to, diff files, though I have to say, be aware, usually when you optimize code, control flow starts to change, and then the numbers will start to be pretty confusing. But if you want to try that, give it a shot. You can runtime attach. That applies also to perf record, by the way. You can just record after you've done the costly startup phase and you just want to look at the steady state over the weekend or something like that, right? This is a quite common technique. And then, as I mentioned before, the timeline is also interactive. You can select one, check the delta between 2 time points, quite helpful. Do note, though, that what we are looking at here is just heap memory, meaning heap memory going through the common allocator things. If you use a managed language like JavaScript, or if you have your own pool allocators that bypass malloc and go straight to mmap or something like that, we will not be aware of that. You can annotate your allocation API using the Heaptrack API header if you want to, and then you would be able to view those things inside the Heaptrack analysis as well, if you want to. Right. How do we use this in an embedded context? First of all, virtualized environments make no problem, because this is purely tracing based. It is not hardware related whatsoever. But one thing that is important to keep in mind is that what we are doing here is we are gathering backtraces at tremendous rates. So you can easily see millions of allocations per second, especially when you do something wrong. The Heaptrack will have a significant overhead in these situations, but it's not 10 times slow, it's maybe 2 times slow or something like that. It's still manageable. But to get this even working, we rely on this great project called libunwind that enables us to get a cached backtrace information very efficiently. Our experience has shown, though, that especially on ARM, this may sometimes break apart. Make sure you use a very recent version of libunwind. Try setting this environment variable to get the EDX unwinding if you want to try that, or reach out for help. But this is it should otherwise just work. Now, one thing though to keep in mind is that these Heaptrack files are by default going to be self-contained and interpreted right away, but that requires access to the debug symbol. So that's not something you would run on on an embedded project in such a way. Instead, what we have to do is we need to separate the recording from the interpretation phase, which is, in the world of Heaptrack, something you have to opt in. It's not the default, contrary to the perf, record, and hotspot way, where it was easily separated already. So with Heaptrack, you would record using the --raw, this is important to keep in mind, on the embedded device. And then similar to perf, you would collect the data to your development machine where you have the SDK, where you have the debug symbols, where you have your side-loaded application, you name it. And then it starts to look very similar to what we did with Hotspot. You pass the paths to your sysroot, your side-loaded application, you name it. And then you pass the --interpret to take the raw file and interpret to produce one of these fully interpreted self-contained data files. And that one you can then visualize on any machine, basically. Again, maybe it takes you 5 minutes to understand that, but it's not rocket science either. It should just work. Even on embedded setups, we've done that a lot in the past. Right. Future outlook. I have lots of ideas, too little time. If you want to hack on this, it's open source. Come hang out with us, and patch is welcome, definitely. Try it out, see whether it works for you. Give us feedback. And if you have any questions, this is where you can reach us, me and my colleagues. And maybe there's time for some questions here as well, if you have any. There's a question.
When you compare this type of instrumental analysis where you are asking for help from, for example, your operating system to take a look at what is happening in the execution, how do you compare that to, for example, the timing that you would get from adding regions in your code?
Mm-hmm. So the question is basically, how do you compare something like sampling-based profiling to instrumentation, where you would annotate your code base or use something like the GCC or Clang instrumentation thingy? So this actually works. The other one doesn't work, because on QNX, for example, you had a sampling-based profiler without the capability to unwind, which was very unusable. So I had to use the instrumentation-based thingy, but that produced us like hundreds of megabytes of data. And because the instrumentation, the outer code paths would include the overhead of the inner instrumentation, and the data just becomes utterly untrustable, in my opinion. Whereas the sampling-based profiling, because it has such a low overhead, actually reflects reality very closely. And I had much better experience using that. And if you look at other platforms like Mac using instruments, or Windows using XPerf and UI4 ETW and whatnot, all of them are using this approach because that's simply what works. So definitely use that and don't use instrumentation, in my opinion. Anything else? Well then, thank you. See you around.